So the meeting is recorded for the benefit of the people who cannot make it for one reason or the other, especially since we had a full, basically 1 hour and 25 minutes on the first one. So people might find that session was kind of long a little bit. And still, we don't really have a full house, and that's fine. We can work with as many people as you guys are. So let me finish that point quickly and then move on. So I came up with this expression. Actually, I moved it a little bit and came up with this expression. Let me just refresh a little bit about the numbers in here, because sometimes this numbers can throw you off. So the units they gave me were in centimeter, not in meters. Okay, if you guys remember, the units 2 centimeters, 4 centimeters. Okay, so assumed x also is going to be in centimeter, and I have now here a centimeter, which is 10 to the negative 2, and I have a centimeter 10 to the negative 2. When I square that, it's going to be 10 to the negative 4. That's why I have a 10 to the negative 4 in here, assuming x now is in centimeters. Same thing in here for the other expression. So I have x 10 to the negative 4. Taking x to the negative 4 and bringing it upstairs will make it 10 to the power positive 4. Remember, 1 over 4 pi epsilon naught is already 9 times to the 10 to the power 9. So I have 10 to the power 13 in here, which I made a mistake. I just realized after that this is not 10 to the power 11, but rather 10 to the power 13. That's what you get when you're on a rush trying to do things. You have to be very careful with this algebra things in there when you're doing them. Okay, so there was an error already in this power law in here, okay? And then you have a nano. Can we guys turn off the audio, please? Okay, so and then I have a nanocoulomb from Q1 and a nanocoulomb from Q3 and a nanocoulomb from Q2 in this combination of nano squared, and nano is 10 to the power negative 9. When I square it, it's going to be 10 to the power negative 18. So I have 10 to the power positive 13 and 10 to the negative 18. That's 10 to the negative 5, okay? And then don't forget I have 5. Why did I get 5 in here? It's because Q3 was a 5 nanocoulombs, and I took Q3 out. So I have Q3, which is 5, and I have a 9. 9 times 5, that's 45. That's 4.5, as I wrote it in here correctly, times power 1. So I'm going to be left with 10 to the negative 4 in here, because remember, I was down 10 to the negative 5, and now down one more time, 10 to the negative 4, because I'm taking one other power from the 45. So the answer, we were off by 100,000. So if we're not careful enough, we're going to get answers wrong. So that's really a good lesson in here to remember to do things right. And then the expression in here. Now I put it x greater than 4. Had x been less than 2, or 0 to be more specific, okay? These numbers would not change much. X equals to 0 is going to be on the other side. So it's going to be 2 minus. And the other one is going to be 4 minus. But x is 0, so this expression that we found is 100% valid even for x equals to 0, okay? Except the signs in here flip. Because if we are on this side, here, Q3 is on this side of 0. This force from the negative 3 coulomb is going to be positive, pulling it towards this way, positive. So the negative 3 coulombs will have a positive sign in it. And this one, Q1, sitting at 2 centimeters, will be negative, going in the opposite direction. So that's going to be a negative. Other than that, everything else should work the same thing. So the answer will be negative 4.5 times 10 to the negative 4 divided times 3 over 16 minus 1 over 4, basically the algebra, okay? Now I have an expression in x that I can plug in whatever x, as long as x actually is not between the two. Because if the x is between the two charges, then I really have to have this one positive because it's pulling toward the negative 3 coulombs. And the other one is positive also, pushing it away. So if I change my sign in here and make this one positive and this one positive, then in that case, also the case when X is between the 2 centimeter and the 4 centimeter. You guys understand? So I took the same problem that was in the example when we made it into a problem that we can discuss the different situations and what's going on with it. Okay? That is not really honestly as important as the second example, which I'm going to rely on you that you're going to go and look at it. The second example is involved a little bit more geometry, that's all. You have two charges, Q1 and Q2. Both of them have 2 microcoulombs. This is a micro now, not a nanocoulombs. This is 10 to the negative 6, okay? Are located at, they give you the X and Y coordinates. The X is 0, that means we are on the Y axis at 30 centimeters away from the Y axis. And they gave us a number already in centimeters, I mean in meters. In the case of the second chart, it's located at X equal to 0. That means it's on the X axis, on the Y axis still, located at a position negative 30 centimeters from the origin. So those are the two charges they gave us. Now what are the magnitude and the direction of the electrostatic force in this case, the electric force that Q1 and Q2 exert on a third charge, which is a 4 microcoulomb charge situated at 40 centimeters away from the origin on the Y axis. So let me go quickly to the geometry to discuss the geometry and how that looks like. So I have a charge in here. I have a charge in here. Both of them I have the same sign. Okay. Somewhere in the middle on the x-axis, we have another charge in here. So this will exert a repulsive force. All the charges are positive. This will exert a repulsive force. And the magnitude of this force and the magnitude of this force will be the same. The same charges on the same charge. This is a different charge, but it's the same charge in the two cases of the forces. So these two forces have the same magnitude, but obviously different directions depending on how big this distance is and how far this one in here. This is 30 centimeters. This is 40 centimeters. So this must be 50 centimeters using the Pythagorean theorem. Square root of 9 plus 16, square root of 25. So that's 50 centimeters. So this distance is 50 centimeters. This distance also is 50 centimeters. So this angle now, we know what it is. We can find it. Actually, it's the arc sine of 3 over 5. And that's the same angle as this one. These two forces have their y components canceling, but they have their x components adding. So the two forces will be either force, it doesn't matter, Q1 times this charge, divided by 50 centimeters, or 0.5 centimeters squared, the 0.5 squared, that is, and then you have 1 over 4 pi epsilon naught, times the cosine of this angle, which is easy, which is 4 over 5 actually from here. That's what the cosine is. And times 2, because you have two of them. So that's in a nutshell how to do that problem. So I'm assuming that you can guys go and look at the book, actually how the book does it, and follow those steps and do these things. These things are extremely important. They're laying the foundation for far more work from this point on. I want you to be meticulous. I want you to go step by step. Do not assume something is understood unless you actually do it and understand it. Do not think that, oh, this is too easy, I can do it, or at least I think I can do it later on. No, that is the wrong attitude about going about doing things in physics. You have to be meticulous. You have to go step by step, okay? I have showed you roughly how to do this thing. I know I didn't go in detail about doing it. I know the book goes also about step by step on doing it. I expect you that you go and actually work out this problem. Should you have a question or it's not clear, please do ask. Do not assume things will be clarified down the road. They only get more complicated actually with more concepts introduced. Do I have, is this clear? Yes? I need the feedback. Okay, good. Some people are already agreeing with this thing in here. Okay. So, so that's the other example that I thought we should talk about in this class in here. You will find this geometry repeating itself a lot in this class, actually. So you really need to pay attention. You'll see it in different places all over the place. So now we know how the force works, okay? So we have an understanding of law. The next concept, the higher up concept that we're going to introduce is the so-called electric field. Why do I do that? Because I live part of my life in Missouri, and does anyone know what the state of Missouri says? I mean, here it's the Golden State. And we're in the Golden State. California is the Golden State. The Apple State is for New York. Does anybody know what the Lone Star State is? Texas. Does anybody know what Missouri is? No? You guys don't know? It's the Show Me State. Okay? So that's what Missouri is. I lived a lot of my life, actually. I was in a college there too. So it's the Show Me State. So always remember to ask the question, why, okay? Prove, show me, explain that to me, okay? So we really need to be on top of that. You really need to have an understanding. So we're going to introduce a new concept now. We just finished the electrostatic force, and we're going to have a different concept that we're going to introduce. At least initially, it sounds cosmetic. It sounds like it's artificial. Why do we have to introduce it that way when we can just deal with the forces? You will see why. Assuming the following scenario. You have a charge in here. You have another charge in here. You have another charge in here. You have many charges. Basically, you put them to one and next to another. And you actually nail them somewhere, or fix them so that they don't move. Because charges, remember, exert forces on one another. And if they are free to move, those forces will cause motion. That's what the second law of Newton says. But if we have them nailed and fixed, now the charges have some sort of a place where we can zero on them. So they are here. They are fixed. They are not moving. And then we bring a charge now to the mixed in here. Bring an external charge next to them. And we ask what force this charges exert on that charge, on that charge, I'm sorry. Well, the force then is easy. Since we have them fixed, we have to hold this one in here at least momentarily before it starts flying. We have to also use Coulomb's law on this charge from different particles and so on and so forth, okay? So that's basically what we're going to do, and then add them up and using the superposition principle, and we're done. So that's one way of doing it. Or what if we really don't have a charge in there to bring in? Just we want to know what effect does this charges have on the space surrounding them? That's the question. So that it's not just a philosophical question, if you wish. It's not we're interested to know what they affect the space surrounding them. We want to know this question because if we do, no, we don't. If we do bring a test charge, we know what this distribution of charges will do to it. So that's where the concept of the field comes into play in here. So we're going to be carrying with us a 1 Coulomb charge, a test charge with us, to test the environment, the geometry, if you wish, surrounding distribution of charges. That's where the electric field comes into this place in here. So what we're saying in here is the following. Distribution of charge of some sort, it doesn't matter which one distribution, and here I drew about 5 or 6 points in there, will change the space, the physical space around it. How do I know that? If I bring a test charge anywhere in space around that distribution of charge, I will measure force there. And that force, I can actually measure it with a force measurement device, and I know how much force is there. So if I don't bring a test charge, that distribution of charge has actually changed the space around it. That's basically what we call the electric field in there. So imagine with me that I'm carrying with me a 1 coulomb charge, which is really nonsense to do. Remember the 2 examples we did, or the 3 examples we did? They did with a nanocoulomb or a microcoulomb. Or 1 coulomb is 1,000,000 times bigger than a microcoulomb, which is a big charge. If you're carrying actually 1 coulomb charge in your hand, this is 1 coulomb charge in here and 1 coulomb charge in here, go back to that expression and see what happened to your hands. You will be subject to a force that is going to be 9 times 10 to the power 9 times 1 times 1, that's 1 squared, which is 1, divided, even if you put your hands 1 meter apart, this is 50 centimeters apart, let's put them 1 meter apart, okay? That's 9 billion newtons. Basically, you're going to be torn apart in no time, okay? So you're not going to do that. So this is a hypothetical. You cannot carry 1 coulomb. 1 coulomb will definitely kill you, okay? So it's a big charge, okay? So you cannot do that. But this is a hypothetical scenario, mathematical, basically, if you wish, construct to help us do this problem. So I have a 1 coulomb. Imagine with me, I have 1 coulomb. Let's say, for example, you cannot afford 1 coulomb for the reasons I mentioned. You can afford 1 microcoulomb, that's fine. You can do with 1 microcoulomb, except you have to multiply your answer by 1,000,000, that's all. If you cannot afford, for example, a 1 coulomb charge still, but all you can, the store, basically you go to them and tell them, can I have 1 coulomb? They tell you, we're fresh out. We can give you only 1 nanocoulomb. And in that case, you say, I'll take the nanocoulomb from you. You bring the 1 nanocoulomb, and the answer we get, well, then 1 nanocoulomb, you just multiply it by 1,000,000,000, that's all. So this is not really a complicated problem, if you wish, if you really want to do it. So it's not really, you don't have to kill yourself over this. So you can still manage with small charges. So assume that we have only 1 coulomb, and we put it in here, and we measure the force on the 1 coulomb. So that's going to be a force. Okay. Force, remember, is a vector. It's a magnitude and direction. So we have its magnitude through a device like this one. Okay. And we have its direction. We know which way it's going to go, the charge. So that is what I'm calling an electric field. Okay, exactly. That's the force that this scale is going to give me on a 1 Newton. If I don't have 1 coulomb, then all I am going to do is multiply the charge you bring in house. That's all. I'm done. So that's what the electric field is. So the electric field is the force exerted on a 1 coulomb charge. So an E, by definition, if you wish, is F over Q. That's it. Provided that the Q is actually 1 Newton. I mean 1 coulomb, I'm sorry. But if you cannot afford 1 coulomb, just multiply the thing with whatever. I mean, if the number is a nanocoulomb, just multiply the thing by 1,000,000,000 and you're done. Okay? So that's really what the situation is. So that's the definition of the electric field. So the electric field is really, I mean, it looks like kind of mathematical only. I mean, we basically played with words and modified the equation a little bit and we came up with something. But it's actually a real modification of the space around the distribution of charge. So it's a physical concept. How do I know it's a physical concept? Because you can measure it. Remember, if you can measure something, it's physics. So this is the electric field. I am sitting right now in my room, and I have my screen on, I have my watch on, my phone on, all kinds of things, electronic devices in here. I have the AC going on. I have some of the lights coming on from outside. I am really inside a huge electric field. Imagine this room with arrows flying every which way. Those are the electric fields, okay? And it's expressed itself in terms of everything that I see surrounding me. The electric field not coming from the devices I mentioned, it's coming from the stars, it's coming from the sun, it's coming from every which way that you can think of. You yourself actually are inside a huge, you're bathing actually inside a huge room of, I mean, it's good that we can see it. If we can see everything of it, I mean, we see part of the electric field actually in terms of light. But other than that, I mean, we are inside a huge, I mean, electric field basically that's coming from which way. The only thing about it in here is that they come in all directions since it's a vector. So if this one is coming one way, okay, and the other one is coming the other way, they cancel more or less themselves. For the most part, basically, they go in every other direction, and on random, they don't have an average value of 0. So that's basically what the electric field. So it's a real concept. And that concept can be measured with a test chart, with 1 Coulomb chart, that is. And you can always do that. The units for the electric field, which is an important concept, we're going to change the units down the road when we find the better definition, if you wish for it. It's going to be the units for the force, which is a derived unit. It's the Newton, which is kilogram times meter divided by second squared. Divided by this unit that we discovered today, which is a Coulomb, as I mentioned earlier, is going to be something that is modified later on in terms of the ampere. It can be expressed in terms of the ampere and the time, seconds. Now, if you wish, 1 unit of the electric field is 1 Newton for every 1 Coulomb. That's basically how you can imagine it. So since we introduced the concept of the electric field, and you have never heard the concept of the electric field, even if you have seen it in other classes, in terms of your sequence for the calc-based courses that you're taking in the college, this is the first time that you're actually introduced to it properly, I would say. It has to be measured. Otherwise, it's not a real physical concept. And I just described a way of measuring it. Bring a charge, 1 Coulomb charge, attached to a mass spring system that is gauged in terms of, scaled properly in terms of newtons. Okay, my thing is on the way. Scales in terms of the newtons, and read what force this thing exerts. Based on that, that is the electric field if you really have 1 Newton and 1 Coulomb. If you have more than 1 Coulomb or less than 1 Coulomb, scale the value that you read from here accordingly. Okay, accordingly. That's basically what you can do. That is what we mean by the electric field. So not only we have defined it, but we found a way of measuring it. Now we're confident it's a physical concept because we can measure it. Okay, that's a key question. When you're taking physics classes, you always have to ask me, ask your instructors, good, great, you just did a good job introducing to us a new concept. Now tell me how you're going to measure that. Because if I fail to describe to you an experiment on how to measure that, I am talking about fantasy. I'm talking about a topic that is not physics. I may be talking about politics for that matter or something else, but not physics. Physics is, as one of you mentioned at the beginning, is based on observation and measurements. If it fails those tests, it's not physics, okay? So that's the concept that I want you guys to have an understanding of. So from now on, Coulomb's law can be expressed according to this definition of the electric field. F equals to QE. So find E first. Once you find E, I can tell you what the force is. Remember the purpose of this force that we just discovered today, the electrostatic force, whether expressed in terms of Coulomb's law or expressed in terms of the electric field. This is the E field you sometimes find me referring to with the, in terms of the electric field. All the purpose of this law is to go back to F equals to ma. So that now we can find A. So we're back to chapter 4 from Physics 4A. So we're back down to the beginning of the book. So now we know, actually most of the work that we're going to be doing in physics is going to rely on this idea in here. So now we have found something, the force that is exerted. From this point on, I can, but remember we're doing electrostatics, so at least initially things are not moving. So we can be basically finding stuff that has to do with equilibrium and statics and things like that, which is down the road from the chapters in that book. But it's still application of chapter 4. So we're not far away from the beginning of the book, actually. We're still in the beginning of the book as far as the concept that we're introducing, okay? Any questions so far? Because this is a big deal, okay? The electric field is a big deal. This course is called the Electricity and Magnetism. We just did 50% of the course if we understand what the electric field is. The other field that we're going to be dealing with is the magnetic field. Do you guys have any questions about this? Or no? It's really the problems usually are not in the definitions or the experiments and things like that. It's in the applications. That's why. Thank you, Chris. Christopher, did I call you correctly or the full thing, or Chris is fine?
Yeah, you can call me Chris. That's
okay,
fine.
Sorry.
No, you're good.
Okay, because I didn't read yet the first assignment that you guys have were supposed still not due until next week or something. So okay. So like I said, the trouble with this class in general, and physics in general, is in its applications. That's why I like to do more and more examples in class. And if need be, especially when we do the lab sessions, we probably can do full problem solving sessions, because I have tendency to give problems from toward the end of the book than at the beginning of the book. I mean, every chapter usually starts with the different levels of difficulty of problems all the way to so-called challenge problems. So in my assignments, I like to give us problems from the challenge. So probably we will do some problems from the challenge section so that we have a full grasp of what these concepts are. Okay. So let me continue with the notes to see where we are in this chapter. So the next thing in here is the electric field, how to calculate the electric field. And down the road, the visualization of the electric field. So let me take one of these examples in here, example 21.5, which is what is the magnitude of the electric field at 0.2 meters from a charge for nanocoulombs. What you need to know in this case, the expression is exactly identical, and I'm not going to do it in detail, is exactly identical to Coulomb's law, except it's missing the second charge. Because all we have is we have the charge that produced the electric field, that's it. Okay? So once we find this expression for the electric field, then we're going to measure. Let's calculate, because there is another point I want to make in here. Okay, yeah. So R is 2 meters. 1/4 pi epsilon naught. That's 10 to the negative 9, 10 to the power 9 times 9, and then the charge is 4 times 10 to the negative 9. So it's from the get-go, the 10 to the positive 9 from 1/4 pi epsilon naught, and the 10 to the negative 9 from the charge, they cancel one another. So this number will be 9. I'm not going to write 10 to the positive 9 because it's canceled by the nanocoulomb. Times 4 divided by the distance squared, and the distance squared is 2 squared, which is 4. Okay? If I did the numbers correctly, so the 4 cancels the 4, so it's 9 Newton per coulomb. That's it. That should be easy enough to do. Okay? So that's this electric field due to a charge at a 2-meter charge of 4 nanocoulombs. Okay? Now, if you bring a 1 coulomb test charge, the 1 coulomb cancel the coulomb in the denominator, and the force will end up to being 9 newtons. If you cannot afford a 1 coulomb, and you happen to bring a microcoulomb, 5.2 microcoulombs if you wish, you multiply 5.2 times 10 to the negative 6 by 9, and now you have the force expressed again in newtons. So you see the utility of the electric field now? As long as you put it in 2 meters. If you put it further away from 2 meters, it's going to be a different story. Now, the reason why I'm saying that is because the electric field is not just real for us, but it's real also for the animal kingdom. And the textbook talks about some of the fish that uses the electric field as a way to basically discover its prey, because it has some of the, it's part of its sensory system is the sensation to minute changes or minute electric fields of the order of 10 to the negative 7 Newton per Coulomb. And that's some of the sharks, at least they are sensitive to that strength of an electric field. Electric field of that order is so small that if you bring this 4 nanocoulomb, remember it's not a 1 coulomb, it's a 4 nanocoulomb, and you put it at 2 meters away from the shark. Remember, part of this thing is to have discussions on the problems, how to solve problems. So I'm doing a discussion here. So think of this problem. Bring a 4 nanocoulomb in here next to that shark, which is sensitive to 10 to the negative 7 Newton per Coulomb. It's going to produce 90 million times higher electric field than what it's sensitive to. So basically, imagine yourself stepping outside. Your eyes are sensitive to light, of course, and somebody put a flooding light in front of you. It's going to blind you. That's what the poor shark would feel. We're just a 4 nanocoulomb sitting at 2 meters. I don't know. I don't do biology, so I have no idea what the reaction of the shark is, or probably it's going to basically tune out that much of the strength of electric field. So probably it's just sensitive, like we are sensitive to certain frequencies in terms of our hearing, for example, below which we can hear, below which we can't hear, and above which we can't hear either. And there is a range in between where our ears are sensitive to hearing. That's why elephants, for example, and other animals, they communicate in low frequency we cannot hear, and some other animals like bats and things like that, they communicate in high frequency we cannot hear. So that's basically some of the things. So that's maybe what's going on with that shark. But I'm just thinking about the poor shark when you bring a very small charge next to it, producing that much electric field, and if it doesn't have defensive mechanism for that kind of thing, it's going to be blinded. Because when we talk about sensory systems, we always talk about, for us humans, about hearing and visual and all of the other things. But other animals, they have different sensory systems like we don't. They can be sensitive to the strength of the electric field, okay? That we don't, we're not. In a sense, we are, but there is another discussion. We'll talk about it later on if we have a chance, or at least probably in physics 3 if we have a chance. So that's another example in here on how to calculate the electric field, okay? There is an error in the book for a problem for the example 21.7. It has 10 to the negative 9. That's incorrect. 10 to the negative 19. Please make that correction, at least in the 14th edition. I have the 15th edition with me, and I didn't look at this specific example. Probably I will look at it, okay? So in this example, what they do in here, they have a battery, 100-volt battery, which we don't know what battery is at this point. Basically, think of it as something that pushes charges around, okay? And it's maintaining an electric field, and they give you the strength of the electric field, which is 1 times 10 to the power 4 Newton per Coulomb between these two plates, okay? And it's asking you, we drop a charge, an electron of charge negative 1.6 times 10 to the negative 19, and we know the mass, 9.1 times 10 to the negative 31 kilogram, released from rest. So basically we'll hold on to it and then we release it from rest. So it doesn't have any initial velocity whatsoever at the upper plate. So we leave it at the upper plate. Remember, the upper plate is negative and the electron is negative. So it's going to be repelled from the negative. The lower plate is positive and the electron is negative. So it's going to be pulled toward the positive plate. So the only motion for this electron is to go from top to bottom, basically coming down, okay? It's going to rain on the lower plate. Is released from the top. What is the acceleration? So we need to find E. E should be straightforward in here. Remember, F equals to ma. So I just restated. I'm not writing, but I'm expecting that you guys, when you solve problems, you're going to write these things, the ones I'm talking about, okay? This is the fact that we know. We know F equals to QE. So from here, we're going to find the acceleration. We have Q, which is 1.6 times 10 to the negative 19. We have E, which is 10 to the power 4, and divided by M, and M is 10 to the negative 31 kilogram. It's going to be a big acceleration. Again, just going with my technique of basically doing things as quickly as possible without having to do a lot of math in here. So we have 1.6, 10 to the negative 19 times 10 to the power 4 divided by 9 times 10 to the power negative 31. 10 to the power 4 and 10 to the negative 19, that's 10 to the negative 15. And 10 to the negative 31, it's going to be a huge acceleration that you're going to find. Remember, the units for the acceleration are meter per second per second. Once you find this one, what speed and kinetic energy does the particle when it travels the 1 centimeter? That's the distance between the plates. So it's going to accelerate, and it's going to reach tremendous speeds in here. So you need to find the electric energy, the kinetic energy. You use the work energy theorem, or you use the conservation of, we don't have an expression. So we shall use just the work energy theorem in this case, or we use an expression that we learned way back before chapter 4, actually, when we were doing the kinematics, namely V final squared minus V initial squared is equal to 2A times the distance traveled in this case. So we have the acceleration, which we calculated in the previous step. We have the distance it's given. We have the initial velocity, it was released from rest. From here, we can find what the velocity is. Take the square root and do that. We really don't need to take the square root whatsoever, because we're asked to find the kinetic energy, and the kinetic energy is 1/2 of mv squared. We already have v squared. All we have to do is multiply it by 1/2 of m, and we have found what the expression of the kinetic energy is. Once we do that, we can answer the last question. Okay, we need to find the velocity because there is a problem in here. When you're dealing with tremendous accelerations like this situation, you need to find the final velocity and make sure it's less than the speed of light. Because you probably heard from physics 3, I know you didn't take it yet, but at least you heard that the velocity cannot be greater than the speed of light. Turns out to be in here several million meters per second, which is, no, is it several million? I think, I don't know. I don't know what the answer is, honestly. But you better need to check the answer to make sure it's not something that is outside of the bigger than the speed of light. Otherwise, this whole oops, did I mute myself? I'm sorry. Yeah, you would say that, look, I know that the speed of this okay, that this speed is what happened in here? Why is my screen not writing? Yeah, that this law doesn't apply then. Do you guys understand that? If it turns out that the speed is so big, closer to the speed of light or greater than the speed of light, you know that this thing cannot be true. There is something wrong with that. See, that part of the discussion you can enjoy, you can do at the end when you're solving problems. And for example, in this situation, it asks to find the speed, and you find a big number. You say, "Oop, it's good. This number is not as big as I thought it could. It's not anywhere near the speed of light, because I know from reading somewhere that any object cannot go so faster than the speed of light. And this is actually very, very small compared to the speed of light. For example, if I find it going 1 million meters per second, is not like going 300 million meters per second, which is the speed of light. Okay? So if the answer is 10 million per meter per second, it's still very, very small compared to the speed of light. Do you guys understand that? So that you have to be, what is it? Yeah, that's basically, you have to be paying attention to these things when you're solving these problems, okay? So that's part of the discussion. Other than that, it's straightforward. Once you find the velocity, you can find the time, which is part of the last question, and the time should be just the velocity that you find divided by the acceleration. Because we're using now the kinematics from before chapter 4, actually from physics 4A. So that's why physics 4A is important for us in here doing this class. Now, it's very important to note something in here, and that is the gravity is neglected all along. okay? Because if we include gravity, these problems will be changed slightly. But how slightly it is, remember from that exercise, it's hardly going to be mentioned. So we are well within our right to exclude gravity from these problems, okay? So gravity does not matter because of this exercise that we did in the beginning. So we can justify that too. Remember, part of the things is to justify your answers, make sense, and things like that. So we're still well within our right to do what we can do, because somebody else might say, okay, which way is the mass? Since this electron has a mass, so probably the Earth also is pulling on it, so it may have a different velocity than what you guys computed. I would tell you it doesn't matter because gravity is so negligible, even from the entire Earth pulling on this electron. So it's still these two plates will dominate more than the case of the gravity. That's one way. The other thing also, you can take the plates and instead of having them sitting like this, just flip them around, and now gravity is going to be minute correction to the direct line in here. So it's going to be a slight projectile that you cannot measure in the lab. Okay. Any questions so far? No? We're going to talk about the lab. Okay, let me finish this. This is a big example. Okay, this is a very big example. The electric dipole. The electric dipole is a concept that we're going to need, okay, throughout this course, and we're going to be referring to the electric dipole a lot. So I really need you guys to be on top of the electric dipole and have a full understanding what it is, because magnetism, the concepts of magnetism rely on it. The antennas on your phone and the antennas in your house for the your TV, if you still have antenna TVs, and even with the others, basically, if you still have dish network, the one that communicates the air, or a lot of telecommunication, they use antennas in general. Antennas is really some sort of a dipole. So you really have to have an understanding of this thing in here. If you're tomorrow stranded in the desert and you need to build an antenna, you have to have an understanding of what the dipole look like or how it works, okay? So telecommunications relies a lot on dipoles. Actually, as a matter of fact, even chemistry and molecular mechanics relies on the electric dipole. The water molecule, for example, and this is probably an example that you already have one of the problems for this chapter, is made up of an oxygen atom and two hydrogen atoms. The oxygen atom has a high affinity for the electrons, will bring the electrons closer to it, and the hydrogen atoms will lose that electron, not completely, basically. There's still a little bit attached to them. That's how the molecule is formed. So what you have in a nutshell, not exactly 2E in here, but the 2E will be sitting in here, and a negative 2E, I'm sorry, did I put it backward? This is the 2E will be here, and the negative 2E will be there, and the distance between here and here is this, what I'm representing in here in this problem, as this distance between the positive charge and the negative charge of what, 4 centimeters. For the water molecule, it's going to be this distance in here, okay? And that's a dipole for you. That's an electrical dipole. So the water molecule is actually an electrical dipole. So the electrical dipole is a very important concept that we have to find the electric field. In this example, which I recommend that you go and still do, even after we do it in class, they give you Q1 sitting at the origin, and it's a positive charge. Q2 sitting at 4 centimeters away from the positive charge. And they give you a point A, which is at 4 centimeters from this charge, Q2, which means that, no, I'm sorry, 4 centimeters. This whole distance is 6 centimeters. No, this whole distance is 10 centimeters. I'm sorry. Let me go back into my algebra correctly. So the distance from the two charges is 10 centimeters, 4 centimeters of which is to point A. That means this distance is 6 centimeters. And point B is situated at a distance of 4 centimeters from Q1 on the other side. And now also they want to find the electric field at a distance of 13 centimeters from each of the charges, meaning that this distance is actually the middle, okay? Because if this is 13 centimeters and this is So this is basically a right angle triangle. I mean, not right. Sorry, it's an it's a what is it? An isosceles? No, an equilateral or an isosceles. I'm sorry, isocel. And then you're supposed to find the so this distance. So this distance is halfway of. So this distance is 5, and this distance is 5. Okay, and you're supposed to find the electric field in there. In the lab, and I'm not sure if we're going to do this lab in here or not, we actually find the electric field everywhere, not just in these 3 specific points. Okay. And once we discovered something called the potential, the potential, the electrical potential, we're going to find the technique, if you wish, of finding the electric field everywhere. Because honestly, if we go about doing the electric field this way, it's going to be very hard to do this problem. So that's why the specific points were chosen for you, because it's easy to find the electric field in these points in this example. So we're going to do the easy way also ourselves. And then we're going to tackle this problem down the road when we empower ourselves with better techniques. We're going to do this problem with in general. Okay, we're going to find the electric field everywhere for a dipole. Okay. So the electric dipole, which is really 2 charges, that's all. I have 1 charge in here, and I have another charge in here. The key thing in here is the 2 charges have the same sign, I mean, same value, and different signs. That's the thing. So one of them is negative, and one of them is positive. This one is Q, and this one is Q. One of them is a negative Q, if you wish, and the other one is a positive Q. Okay, that's what this problem is. One of them is a negative, and the other one is a positive. And both charges in this case are 12 nanocoulombs. Okay. So think of them that they have the same numerical value in terms of charge, but they come in different shapes, that's all. Different size. And now this distance, I'm going to use the same thing as the book uses it, and I'm going to call it D. The distance from the negative to the positive. Let me repeat. The distance from the negative to the positive is D. It's not the distance. I know it's a distance, so it's the same number. Okay, it's the same from positive to negative to positive, the same distance. It's a scalar. I mean, it's a absolute value, if you wish. But later on, we're going to promote this scalar, this number, into a vector, especially if we're in space. And then the key words in here, negative to positive, not positive to negative, always from negative to positive. So this vector, when we promote it to a vector, this quantity, when we promote it to a vector, you have to remember this order, that you're going from negative to positive. Okay. Once you do that, then you're in good shape. Okay. That is a characteristic. So in the case of the water molecule, it's that distance basically. It's about slightly more than an angstrom, or okay, 2 angstroms if you wish, okay, of the order of 10 to the power -9 or something meters. Okay, so we have that, and we're going to find the electric field somewhere in here. So I'm going to take my origin slightly different. I'm going to take the origin in between them. So this distance is d over 2, and this distance is negative d over 2, and I'm right in the middle. Okay, and I'm going to find the electric field at the distance x in there. X can be positive or negative, so it doesn't matter. We can go and replace the value for x later on. So let's find what the electric field is. I need to know this distance. Okay, this distance is clearly, this is my origin. This whole distance is x, and this distance is d over 2. The distance between q and the point where I want to find, this is the point where I want to find the electric field. It's at a distance x from the origin, is x minus d over 2. That's 1. The other distance I'm interested in is this whole distance. Okay? And that distance from the negative charge all the way to where I want to find the electric field, that distance is x plus d over 2. Do you guys visually see it? Do you see the difference between the two? So I took my origin away. I'm trying to find the electric field in these 2 points. I promise this will be the last one, okay? Because I know we're getting a lot of materials right now. Okay? So I want to find where the electric field is in there. So the electric field, due to the positive charge, is going to be pointing in the positive direction. This way. It's pushing it away. If I bring a test charge of 1 coulomb, it's going to be repelled from the positive charge. The negative charge is going to be pulling it towards it. That's the only distinction I have to make. From the positive charge is going to be positive. From the negative charge is going to be negative. And that's it. So once we do that, the two charges are the same. The 1 over 4 pi epsilon naught is the same for both of them. The Q is the same. It's going to be positive for the positive charge. Remember, it's x minus d over 2 squared. And minus, let me move this thing away because it's on there. And bring this thing. 1 also over x plus d over 2 squared. One of them is positive for the positive charge, and it's at the distance x minus d over 2, and the other one is negative because it's a negative charge, and it's x over d over 2 squared. Does everybody agree with me on this expression or not? Do we have any questions so far for the electric field? Because this is key. Do you guys agree on this expression? Yes or no? I need the feedback. Okay. Okay. So if you have doubts, oh, there is no 9. I'm sorry, Q. My notes sometimes sound like it's a 9. Sorry about my handwriting. This is a Q. Okay. Because this is a Q and this is a Q. So think about it. 1 over 4 pi epsilon naught times Q over the distance squared plus 1 over 4 pi epsilon naught times Q, but the other Q is negative now, over the distance squared. And the distances are given by this expression. Does this answer your question? Jaden? Yes? Okay, good. So sometimes my handwriting is kind of sloppy and things look different than what I had in mind. Okay? So we have that expression. Now we're going to do a little bit of algebra in here. And I want you to go back as far back in time as you can go with the algebra in here. We're done, actually. We're done with this calculation. If you're really curious, I'm sorry? Do you have any question? Somebody? No? If we go back into the problem, plug in the numbers, we have the answer to at least the questions, the parts A and B. Okay, we're done. Because we have X. Let me go back. We shifted the origin, that's all. Okay. So if we plug in the numbers after I shift my origin, I can find the answer to this question for parts A and B. We're done with that example completely 100%. And if all you want to do is that example, you're done. But I want to go a step further. I want to take the electric dipole where it needs to be because it's part of this chapter. So I want to push it a little bit. So I'm going to find the common denominator, which is the product of the two denominators. And then I'm going to find the difference of this expression minus the other expression. Basically, we do the algebra, that's all. So the electric field now is Q over 4 pi epsilon naught. The common denominator is x minus d over 2 squared times x plus d over 2 squared. The numerator will have an x plus d over 2 squared minus x minus d over 2 squared. Remember, this one, they shift around a little, okay? That's it. Now, I have something that we learned way back that says a minus b times a plus b is equal to a squared minus b squared. Do you guys remember this identity from your high school? If not, it's easy to expand in here. A times A is A squared, minus B times plus B, it's minus B squared. And the cost terms, they cancel. A times B is AB, minus A times B, that's minus AB, and they cancel. So this is easy to prove. So this is what I'm looking at in the denominator first. In the denominator, I have x minus d over 2 times x plus d over 2, the whole thing squared. So that's exactly what I have in the denominator. I have this expression except that it's squared. So I'll end up with x squared minus d squared over 4, the whole thing squared. So I can use this identity and fix the denominator. So the denominator, that's q over 4 pi epsilon naught, x squared minus d squared over 4, and the whole thing squared. Because I have x minus d, which is this term, and I have x plus d over 2, which is this term. When I multiply them by themselves, after I remove the powers of 2 first, I have x squared minus this whole thing squared, which is d squared over 4. But don't forget, I have a power 2 in here, which I'm going to restore back. So that basically takes care of the denominator. In the numerator, though, I have the second side of this expression. I have this squared minus this squared. So I'm going to combine them now and write them as this term minus this term times this term plus this term. So I'm using the same expression twice, except I'm using it one way in the denominator, I'm using it in the way in the numerator. So I'm using the same expression 2 times. So watch the numerator. So in the numerator, I have this expression squared minus this expression squared. So my A now is x plus d over 2. So x plus d over 2 plus, or I'm sorry, Control Z, minus x minus minus, that's plus, d over 2, times x plus d over 2, that's my A, plus x minus d over 2, that's my B. Okay? Of course, this d over 2 and this d over 2 cancel, and I have 2x in the numerator. And in this expression, the x and the x cancel, and I have a d over 2 and a d over 2, which is d. So at the end of the day, after all this dust settles, I have the electric field as q over 4 pi epsilon naught. Remember, I have 2x, and I have a d. I have a d from here because I have d over 2 and a d over 2, that's d. And I have 2x from the other one. So I'm going to write it 2 times d times x divided by x squared minus d squared over 4 squared. The 2 and the 4 cancel. And the final expression, I'm going to write it as E equals to Q times D over 2 pi epsilon naught times x squared minus d over 4, d squared over 4 squared times x. A dipole really is useful when you are far away from it. Okay? That means x is very big compared to d. If it is the case, before I do that, let me define, as your book defined, P as QD. This is called the dipole moment. The dipole moment is a vector, actually. It's not a scalar. It's the product of the charge and the distance between the two charges. That's all. It's a vector defined, in this case, as the product of the charge and the distance, and it points from the negative charge to the positive charge. Remember what I was saying earlier, that it's very important that you guys need to remember this thing? That is basically why that's from the negative to positive comes in. It comes in the dipole moment. So this is the so-called dipole moment. Okay? So in terms of the dipole moment, the electric field E, the magnitude of it, is P times X over what is it, 2 pi epsilon naught times x squared minus d over 2 squared, okay? That is basically in a nutshell what the electric field on the same axis of the two charges. So if you bring me the water molecule, and if you all on the same line that points from the oxygen molecule to the oxygen atom to the middle of the two hydrogen atoms, that is what the electric field is going to be equal to. Far away from it, this quantity is negligible, so I'm going to drop it, and I will have x squared to the power 2, that's x cubed, and the x to the power 4, I'm sorry, x to the power 4 and x in the denominator. So at a distance very far away from it, this is basically how much the electric field is. So when x is very large compared to d, this number will be negligible, ignore it. So it will be x squared to the square, that's x to the power 4, and you have an x in the denominator, so that's basically, it's a cubic law. I promised you guys to stop in here, so I'm going to stop in here. This is basically for the electric dipole. We did a lot today. We still are not done with the electric dipole. We need to find the torque exerted by a electric field on a dipole. So think of these two charges sitting by themselves, one on one side and one on the other side, and I bring them inside an electric field. And I want to find the effects of the electric field on this dipole. This is the rigid structure. So this is a structure. The two charges cannot go flying which way. So they have to somehow stay to one another. So we'll see that the electric field exerts a torque on it. We'll have to find that torque. If I force my dipole to stay against the electric field, I need to expend of an energy. I need to find what that energy is. And then we have to find, so this is two charges. Then we're going to do more exercises with this chapter. We're going to find the electric field due to a distribution of charge. We're going to find the electric field due to a ring. So basically think of a ring. I don't have any rings in here, do I? And throw in, sprinkle some charges on it and find the electric field right in the middle. And then find the electric field of basically a line like this one. Take this one and sprinkle charges on it and find the electric field somewhere. And think of this line when it becomes infinite and find the electric field on it. And also we're going to find the electric field created by a disk, not a ring. A ring is open. A disk, basically, how much the electric field produced on the axis of symmetry. And then at the end, we're going to find the electric field by an infinite plate. Basically, how much the electric field is going to be on an infinite plate. And then I bring two plates, one to the next to another, and find the electric field they produce. Okay, that's going to be an important device later on for me, for my electrical circuits. Okay, so this is in a nutshell an introduction to the course. We're building concepts in here. When we meet on Wednesday, we're going to meet at 12:45. We're going to finish this discussion hopefully by then. And I'm hoping that you guys are reading the chapter and also doing the exercises in there and doing the problems from the mastering physics and also doing the problems from the homework. Reach out to me. The best way to reach me is actually through Canvas. And I should respond to you right away, unless I am in a class like this one. I know several of my other students, they have been sending me messages while we were in session, so I couldn't answer them. So if I'm not answering you right away, expect me to be busy with somebody else. And I have also office hours. Please visit them. They are on the syllabus. Ask me to meet, and I'll be more than happy to meet and go through some of the examples or the questions that you have. And we'll discuss them. Now, in terms of the lab, we're going to do lab virtually on using mainly GeoGebra, okay? You will have specific instructions on how to do the lab, and you will have lab report forms that you're going to be filling, and I'm going to go specifically also on those things step by step on how to do them. And hopefully you guys finish these things. Don't forget that you have the discussion assignment, which is due next week, I think. But the first part of it, the initial replies, are due this Saturday. Any questions before we call it a day? If you don't have any questions, When we do the lab sessions, they're going to last for a long time. When we do the lecture sessions, they last only for their allotted times. And I guess I'll see you Wednesday, unless you guys have something for me. No? Okay. Have a good rest of the day. Thank you.